Hello students, welcome back. So in the last video lecture we applied Laplace transform to solve differential equations governing vibrations. So we solved spring mass system and spring mass damper system both for free vibrations, meaning that when you say free vibration, that really means there is no external applied force basically. Yeah. Okay, so what we yesterday studied, that can be applied to solve also the underdamped condition. Okay, so we solved yesterday the critically damped condition, then the overdamped condition. So underdamped also we can solve. So underdamped condition, and again the equation remains the same, and equation was x double dot plus 2 zeta omega n x dot plus omega n square equal to 0, and for underdamped condition our zeta is less than 1. Okay, so if that is the case, then let's look at how this will look like. So we will follow exactly the same method that we saw that we did yesterday, and based on that we are going to find out what the solution will be. Okay, so this is one equation. However, all differential equations should be accompanied by some kind of like boundary condition or initial condition. See, this is a time dependent problem, so this is a initial value problem, it is also called. Okay, so in the initial condition we want, so initial condition we can say x at t equal to 0 is equal to x naught, and x dot at 0 is v naught. Okay, so these things are known for us. So what is the x at t equal to 0, what is x dot at t equal to 0, they are known. So together we have to solve them, all the three equations together. Okay, now what we will do, first thing we will apply the Laplace transform here. So 2 zeta omega n plus omega n square equal to 0. Okay, or we will write the same thing that we did yesterday for this one. So L for if you take the Laplace transform of x double dot, you get s square xs minus s, then you have x 0 minus you have x dot 0. So you get for this one now plus 2 zeta omega n. Okay, so sorry, here it should be x dot and here x, so x here. Okay, x dot and x here. Okay, so x dot x we have added here. So then Laplace transform of x dot, so that makes it s x s minus x at t equal to 0. So we get this, and plus this one, so plus omega n square x s is equal to 0. Okay, so we have to separate them out. So we say or, and then x s multiplied by s square. Okay, then we have 2 zeta omega ns, 2 zeta omega ns plus omega n square. So this with a coefficient xs, then plus we can write all other things on the other side. So on the other sides we get s x at 0 plus x dot at 0, and then this one plus 2 zeta omega n and x at t equal to 0. So this we get. Okay. Now or x s equal to, we get s x 0 plus x dot 0 plus 2 zeta omega n x at 0 divided by, we have s square plus 2 zeta omega n s plus omega n square. Okay. Or we get x s equal to, now we have to here rewrite it as we did earlier yesterday for overdamped condition. So same kind of thing we have to do, but we have to keep in our mind that zeta here is less than 1, so accordingly we have to rewrite that. So s x 0 plus x dot 0 plus 2 zeta omega n x at 0 divided by, we have s square. So here we rewrite as s plus zeta omega n square. So this makes it s plus 2 zeta omega n s, this one. Okay, plus zeta square omega n square. So we have to subtract here zeta square omega n square, and we have to add this one omega n square. So this is how this will be. Okay. Now, since zeta is less than 1, so we can write like this. So equal to s, then we are going to write, let's have one of these this side, so this is going to help us later actually. So we write x at 0 multiply plus s plus zeta omega n, okay, like this one, plus x dot 0 plus zeta omega n x at 0. So this divided by, we can write it as s zeta omega n square, okay, and then we can write plus omega n square 1 minus zeta square. Okay. Now in video lecture number 2, we call this one omega n square multiplied by 1 minus zeta square as omega d square. Okay, so we can write this one as so we are going to simplify further. So we write x naught, and then we have here s plus zeta omega n divided by s plus zeta omega n square plus omega d square. Okay, so this is 1 plus we have here, we can write it as x dot 0 plus zeta omega n, then x at 0, okay, and then divided by omega d, we are doing it, okay, omega d because we need it, multiplied by omega d. Okay, so we have this thing taken from here, divided by omega d here, because this omega d is yes, that's why we want to arrange like that, and s plus zeta omega n square plus omega d square, where omega d is nothing but omega n times 1 minus zeta square. So that's what we also did in lecture number 2. Okay, so same thing we are writing it here. Okay, so we get like this one. Okay, so now if you xt equal to L inverse XS, right? Okay, and the value will be, first is this one. Okay, so if you take the inverse Laplace transform of this function, s plus zeta omega n divided by s plus zeta omega n square plus omega d square, what do you get? Okay, so this is a standard actually, so we write here the value will be x naught times e minus zeta omega n t multiplied by this term will gives you the cos actually, yeah. So okay, so I've written here x at equal to 0 at x0 like here. So okay, so x0, so we have like this one, and then it will be cos part here, so cos, and then cos will be omega d, so cos omega d, okay, and then plus this value, the whole thing here, okay. So plus this will be x dot 0, we call it v naught, so let's write v naught here, so v naught plus zeta omega n, and x at 0 is called x naught, so write x naught here, divided by omega d, okay. Okay, then inverse transform of this one, okay. So inverse Laplace transform of this one is nothing but cos, so multiplied by, I will write here only cos omega d, okay. So xt will be x naught times since zeta omega n is also there, so we have to multiply here with this term as well, okay. So value will be not only this but also, so multiplied by e to the power zeta omega n t multiplied by sine omega d. So this is the solution basically, yeah. So we can write it further here. So our the final expression will look like something like this one. So we will write here xt becomes equal to x e to the power minus zeta omega n. Okay, sorry guys, we also have to write t here, so omega d alone will not be there, okay, so it has to be multiplied by t, okay. Okay, so here also omega d multiplied by t, okay, so this is correct. So e to the power minus zeta omega n t, so let us keep that in common, and then we have x naught plus cos omega d t, okay, so okay, then we have plus and then we have this, so v naught plus zeta omega n x naught divided by omega d, okay, and then we have sine omega d t, like this. So this is the final expression, and where x naught and v naught as we wrote earlier, so x naught, where x naught equal to x at t equal to 0, or v naught equal to x dot at t equal to 0. So this is the final expression for the solution for the for underdamped condition, okay. So where zeta less than 1, so That's the underdamped condition. Okay. So once we have the expression for the displacement for underdamped condition, we can simplify it further. When you say simplify it further, meaning that we can rewrite this one as xt is equal to E minus zeta omega nt, okay, and multiplied by sine. So here we can write it as x, let's say here x naught, x is x naught e to the power minus zeta omega nt multiplied by sine then omega dt plus phi. Okay, how? Provided we have a value of phi here, so x naught, if we take it as sine phi, okay, so where sine phi is equal to x naught, okay, and cos phi, oh, okay, so not x naught, just has to be also divided by this, the whole thing, okay, so root under here, and then x naught square plus we have this v naught plus 2 zeta omega n x naught divided by omega d whole square, right? Okay, so, similarly cos phi we have to write as cos phi is equal to, we'll have v plus xi omega n x naught over omega d, okay, and then we'll have divided by root under, and we have x naught square plus v naught plus zeta omega n x naught divided by omega d whole square. Okay, so if we write like this, sine phi equal to x naught over square of this plus square of this, and the square root of that expression. So then we can write this xt, the displacement, as x naught, where x, what is x naught? X naught is this one, so we write x naught is equal to root x, big X naught, x square plus v naught plus zeta omega n x naught divided by omega d, okay, the whole square. So basically what the meaning is, we get sine phi equal to x naught over capital X naught, yeah, and cos phi will be equal to v naught plus zeta omega n x naught over omega d x naught, yeah, or tan phi equal to x naught over x naught multiplied by omega d, then v naught plus zeta omega n x naught. Okay, so we can write it like this one, and this is convenient. This is because then you know the expression. If the expression is like this one, so we write down like this: xt equal to x naught e to power minus zeta omega n t, then sine omega dt plus phi. If the expression is like this one, then you know that there are this can be visualized as a sinusoidal function. However, the amplitude is decreasing. Yes, the amplitude is decreasing with time. So we have a like exponential with negative term. So this will be changing. So, but if there is a phi here, so if you have to plot, how will you plot? So it will look like something with respect to t. At t equal to 0, you have x naught here, and you have x naught sine phi, basically. Here t here also equal to 0. So you start with here. It will be something like this value, and this value is x naught sine phi. Okay. Okay. And this will go up. From here it will go, right? Okay. Now this is the initial value of this one, okay? And then it will, from here it will go up, and so this is what it will go like this one, okay? What you will see here is basically there is this function. So this is the which function? This is e to the power minus zeta omega nt function. Okay, rather it will be x this one, yeah, x naught times. Okay. So this envelope will be x naught e to the power minus zeta omega nt. So here this value is x naught sine phi, but this value will be the x naught. So this will be x naught value. Okay. Since at t equal to 0, the whole expression becomes, this becomes x naught. So that's why this value from where this function starts will be x naught. However, the point where the sinusoidal function starts will be x naught sine phi. So this point is x naught sine phi. Okay, that's what I wrote here. So, okay. Okay, so we know that this is decreasing, and this has some information there. Okay, so what is the information? What we see here, omega dt, that really means it has got a time period. And what is a time period? Let us say time period is tau d. So we have omega n, not omega n, omega d. So omega d equal to 2 pi tau d. Yeah. So that means tau d is equal to 2 pi over omega d. And omega d, we know the value is 2 pi divided by, we have omega n multiplied by 1 minus beta squared. So that's the omega d. Okay. Okay. So what we see, it has a time period, and the time-wise distance between all the peaks, for example, from here to here. If I ask you what is the time, okay, so time will be tau d only. Right? This is because this is omega d here, and tau d equal to 2 pi by omega d, and because of that, this is time period. We write here time period, and because of that time period, this will be constant. So from here to here, the same tau d. From here to here, tau d. From here to here is the same. So from, if you measure in terms of time from here to here, this will be tau d only. Yeah. Okay. Yeah. Second thing, we can also notice that there will be accordingly some information also about the zeta is there. Okay. So we will see this one now. Okay, so the topic that we are going to study is called logarithmic decrement. Okay, so for the underdamped condition, we know that xt is given by x naught e to the power minus zeta omega n t, and then we have sine omega d t plus phi. So all those things we already studied. Now, how it looks like? This looks like that also we have studied. If this is a with respect to time, if you want to plot this one, so there will be envelope which will be like this one from both the sides. Okay, and this will be for minus x naught e to power minus zeta omega nt. This will be x naught e to power minus zeta omega nt, and between that there will be sinusoidal function which will go like this, and okay, eventually this will be 0. So this is how the solution will look like. That really means that, what is the physical meaning of that? If you have a spring damper system, K and C here, and if the zeta is less than 1, okay, so if it is under damped condition, that really means if the C is small enough, you know, so okay, if C is small, then if you give some disturbance, let us say you have brought it here and you just released it, so then it will start oscillating, but eventually it will be 0. So that's why it will start oscillating here and slowly this will be 0 like this. That's what the meaning is. Okay. Now the question is, can we find out, for example, zeta from here? Okay, it depends on the equation, depends on zeta, you see. So this decreases here, and zeta plays a role because zeta times omega nt is there. Okay, so that means some information is there. Let us say we have a system, we have k and m known, and we don't know what is the value of c, and that we have to find out. Can we do some experiment? Let us say maybe we stretch it little bit and release it, and we record how the displacement is with respect to time, which will look like something like this one, and from that plot can we find out what is the value of zeta. In fact, that you will be doing in your lab. Okay, so design lab 2, in that there is one experiment where you have to find out what is the value of c, right? This is inverse problem basically. Yeah, okay. So for doing that, let us say you have 2 consecutive peaks we are talking about. Okay, so this one is, say, t some value here, t equal to, let's call it TA. So let's A and call it B. So TA, and this one will be T equal to TB equal to T equal to TB equal to TA plus, what is the value from here to here? This is tau d, as I said earlier, so plus tau d. Okay, now we will put this value here. So what do we get? We get x at a point at A will be equal to x naught e to the power minus zeta omega n t a, then sine omega d t a plus phi. Okay, then xb will be x naught e to minus zeta omega zeta, and then we have omega n t b, but we know that tb is nothing but ta plus tau d, so we write ta plus tau d, and then here also multiplied by we will have sine omega d, and then ta plus tau d plus phi. Okay, now there is something called logarithmic decrement, which is defined definition. Okay, so logarithmic decrement meant is defined as delta equal to natural log of xa over xb. This is how it is defined. Okay, so let's find out. Okay, so if this is the value, we have to find out delta. How will we find out? So delta equal to xa, we write this divided by this term, and we see what the value is. So let's say ln, and then we have x naught e to power minus zeta omega n t a, then sine omega d times ta plus phi divided by x naught e to power minus zeta omega n ta plus tau d sine omega d t a plus tau d plus phi. So this is how it will look like. Okay. Now the next thing what we have to do is, actually we have to see which all things cancels out here. So x naught cancels out this term, and from we divide like this one cancels out. What we see here, omega d ta plus tau d. Now you see here ta, like what is the value of what we see? We can write here where sine omega d ta plus phi is equal to sine omega d ta plus omega d times tau d, omega d times tau d plus phi. Both will be equal. Why? Because tau d equal to 2 pi over omega d, or omega d is equal to 2 pi over tau d. So that means this multiplied by this is nothing but 2 pi. Okay, so where here we did earlier, right? So where tau d is a time period which is equal to 2 pi into divided by omega d, hence tau d times omega d equal to 2 pi. So see here, sine omega d times ta plus phi equal to sine omega d times ta plus 2 pi. This one is 2 pi plus 5. So both are same. So this term, sine term, and this sine term that are same cancels out. X naught cancels out. What you have is just this divided by this one. So delta is nothing. From here you get delta equal to ln, and then you have e to the power minus zeta omega n ta divided by e minus zeta omega n ta plus tau d, like this. So final expression will be equal to ln, and then you have, what do we get? We get simply e to the power zeta omega n tau d, right? Or equal to zeta omega n tau d. So delta equal to simply is equal to zeta omega n, and what is the value of tau d? Tau d is 2 pi over omega d. Yeah, so will be 2 pi zeta omega n over omega d. So 2 pi over omega d equal to tau d. So 2 pi zeta omega n over omega d. But omega n over omega d is what? Omega n over omega d is 1 over zeta square, 1 over root under 1 minus zeta square. So this will be 2 pi zeta divided by root under 1 minus zeta square, simply, right? Because omega d is equal to omega n multiplied by 1 minus zeta square, right? This is the relation we saw 2 days back. So hence omega n over omega d is equal to 1 over 1 minus zeta square. So this is what you get, right? And hence you get 2 pi times zeta divided by 1 minus zeta square. So delta, if you know this logarithmic decrement, if you know the logarithmic decrement, that you can measure from your experiment, as you will be doing in your lab, okay, in next semester. And that if you know, then this side you have just zeta only. So 2 pi times zeta divided by 1 minus root under root square root 1 minus zeta square. So you can solve for zeta. You can find out what the zeta is. If zeta is very, very small, then 1 minus zeta square will be equal to 1 minus zeta square will be equal to close to 1, you can say, and in that case it will just equal to 2 times pi times zeta also. So you can do this kind of thing. So the logarithmic decrement means that delta, that means the natural logarithm of ratio of 2 consecutive peaks, the amplitudes, and that is a constant value. That constant value depends on, is not really constant, but depends on the c, because that zeta is what? Zeta is equal to c over 2 root km. So if k and m are known, yeah, and you have this experiment you have done, you find out from here what a delta is. Delta tells you zeta, and you know zeta equal to c over 2 root km. You know km and m, you can find out c. Okay, so this is what it is about. Okay, so far we have been working with viscous damping. So viscous damper, right? Viscous damping. Okay, and we denoted it like this one, and we knew that this F is proportional to the velocities, F equal to Cx star. Now this is viscous damping, how the behavior is. We have already simulated, analyzed with that. There is another kind of damping which is known as Coulomb damping. Coulomb damping, okay. So Coulomb damping is the friction basically, right? So this is between the two surfaces. This is actually equal, friction. This same friction as you have studied, right? So if there is a M here, and then if we put like this one, if so whatever the reaction is R, and if you try to move it this way, right, so there will be a frictional force equal, if is a force equal to Fd, and that will be, this friction force will be equal to this force. If you apply force equal to, you apply this force, so this frictional force will be maximum equal to, so we write like this one, Fd equal to F if, okay, if force is less than equal to mu r, right? Okay, so this is frictional force. Fd is the frictional force. Frictional force. So you applied a load here, a force here, and then you, let's say you start from 0. So you have 0. So the Fd will be 0. If you increase more little bit, then the value will be also equal to F. As long as this F is less than mu times R, the Fd equal to F. However, when the value is, if F is more than mu R, then this may start moving, and the dynamic friction will come into picture, right? So assuming that the dynamics and static friction are both same for this case, then you will have, in that case, if F is greater than mu R, in that case the Fd will be equal to mu R1. So the Fd max is mu R. So Fd equal to F as long as F is less than mu R. However, Fd can be maximum mu times R only. Here we are assuming both a static and dynamic friction, both are the same. Okay. Now what we want to do here? We want to do something like this. Let us say you have a spring here, okay, and you have a mass here like this one, and there is a friction here. Okay. Here it will be a contact of two surfaces, and because of that there will be Coulomb damping. Okay. If that is the, let us say this is M like this one. Okay. So, or could be some weight as well on top of that, there may be additional weight and so anyway. So if that is the case, and what you are doing, you are stretching a bit and then releasing it. And now we want to simulate this condition. Okay, so we want to actually do analyze it to find out how the motion will be. This is complicated because what happens is the force, if this is going this way, then force will be acting in the opposite direction, but force will be constant force. Force will be equal to Fd, because as long as it is moving, the force is constant. F equal to Fd, where Fd equal to mu times the resisting force, which is Fd, is equal to mu times R only, which is actually constant, right? So if you compare with the viscous damping, the force is not constant. Force is proportional to velocity. Yeah. So there, in the equation, these are part of the differential equation. In this case, constant term, but you have to change the sign. If this is going this way, then Fd will be opposite side. If the velocity is this way, Fd will be other side. There was no problem in this viscous damping, because automatically, depending on which way the velocity is, automatically the force is applied, right? So if the velocity is this way, the force will be opposite to that. Automatically in the equation, automatically it takes like that. Okay. So in any case, if we want to solve this kind of condition, this Coulomb damping with a spring mass system, then how will we do it? Okay, so this we are going to do now. So we will have the same setup as we had earlier. So there is a spring like this one, okay, and there is a mass here, M here, and then what? So let us say this is the X goes like that, and there will be opposite to the X, there will be a force Fd which is going to apply like this. Okay. Okay. So the equation, if it is going this way, okay, then equation will be mx double dot plus kx, okay, and here Fd. So you can draw the free body diagram. So stretched like this one. So you have kx here. So this is x here, okay, and then the Fd is also this way, okay. So opposite direction in the negative direction, because this depends on again the velocity though, I mean the direction of the motion, right? So if we have velocity this way, Fd will be if x dot is positive, right? Then it will be like that, okay. So right now, if assuming x dot is positive, then in that case we have mx, we will have kx minus Fd is equal to mx double dot, and hence we will have equation mx double dot plus kx plus Fd equal to 0. Okay. Now let us say when it goes here and then this is coming back now. It goes, stop somewhere, then it will start coming now. When it start coming, then it is still x is positive. However, the x dot is negative. So x dot is coming dot, x dot is negative. And in this case, what happens? The Fd will be this way. So Fd will be here now. Okay. Okay. So what is the equation in this case? The free body diagram, if you draw, in this case will be kx, because this is still, it is away from its mean position. So still there will be a stretching. So kx will be like this one, but Fd will be like applying like this one, and hence you get the equation Fd minus kx equal to mx double dot, and hence you get mx double dot plus kx minus Fd equal to 0. So what you see that depending on which way, if the mass is moving positive direction, this equation will work. If the mass is moving in negative direction, this direction, then this is the equation which this will follow. Okay. If that is the case, then how to solve the problem? Okay, that's what we will do now. Okay. Okay, if you compare the Coulomb damping with the viscous damping, what we see is this will be opposing the motion. So if the velocity is this way, the Coulomb damping, the resistive force because of the Coulomb damping will be the opposite of that. And same thing happens with the viscous damping as well. If the velocity, if it is going this way, some velocity going this way, the force, resistive force is the opposite. Yeah? So both the cases is the same. It is try to oppose the motion, basically the velocity. If for viscous damping, if for under damping conditions, if you had something like this one, right? So you had going like this one. Yeah. You expect the similar kind of result for this also. So meaning that you have a spring mass damper system, and here there is a friction force mu, for example, and then what you are going to do, you stretch it and leave it. It will go, you know, and while it is moving, there is a friction force there, and there will be, because of friction, there will be energy lost. So finally the kinetic energy is going to be lost because of that. The energy, total energy is stored. Okay, so there will be, if you, the kinetic, let us say if it is smooth, then what happens? There is no mu. In this case, if mu equal to 0, then there will no any loss of any energy. In that case, this will be equivalent to this only, right? So this and this system will be equivalent when mu equal to 0. But when you have mu equal to not 0, then what happens? There is a loss of energy. So for this case, if you oscillate it, it will keep on oscillating. Once disturbed, it will keep on oscillating like this. The amplitude remains the same. Now try to, you know, waste some energy. Every cycle some energy will be going out. So because of that, what will it will do? The kinetic energy, the potential energy, it will lose, right? And hence the kinetic energy will also lose, right? So in this case, if mu not equal to 0, what we expect from there is, instead of going this one, there will be some kind of loss. So you will start with that, and it will be losing like going like this one. How exactly, that we have to find out. But this is how it will look like, something like this one. And this also for this one is for the, what I showed here, this one is for viscous damping. What do you see here, this exponential? Here we don't know whether it's the exponential or linear or what, that we have to find out. Okay. But in any case, if this is the, we are trying to get the approximate solution for Coulomb damping, right? Okay. So let's call it this one as x1. We call it this one x minus 1, and this one we call x2, like this one. Okay. Now see here, from here to here it will come. What is the total? What you see here is displacement, here it's time. Total displacement will be equal to here x1, and this one is x minus 1. So x minus 1 is actually negative number, right? So it will be negative number. Right? So like actually this value here, like x1 is a positive number, x minus 1 is positive number. So basically the total displacement is basically total displacement between, let's call it A, B, C. Okay, from A to B, position, okay, will be equal to x1 plus x minus 1, right? Amplitude here is x1, amplitude here is minus 1, right? So minus 1 is a subscript actually. Okay, so this is the total displacement. Means it goes from here one stroke. Means it is moving from here to here. While it is oscillating, this mass is at point A which is at rest. So at this v equal to 0, and then from here it comes to point B. Yeah, let's say point B is somewhere here, B, and here also B equal to 0. So from here to here it comes directly. Yeah, okay. So in that case, what do we get? We have potential energy in the both the situation, right? So total displacement is this one, and what do you get? You get from this position to this position, and this position, let's call it x1. This position you call it x with subscript -1. So total displacement from here to here will be given like this one. Total work done accordingly. Total work done will be, if Fd is the Coulomb, the force because of the frictional force. Yeah, so work done equal to Fd times x1 plus x minus 1, where Fd is the frictional force due to the Coulomb damping, basically, right? Okay. Okay. Now, if there were no frictional loss, something like this one, b equal to 0, then why we expect? We expect that this value and this value both are same, right? Equal. Both are equal. However, if there is a loss because of the friction, this amplitude will not be the same. Okay. So this amplitude from here to here will not be equal to here to here. And why? There will be loss because of frictional work. Yeah. So this loss will be basically nothing but equal to frictional this total work done. So what I mean to say is energy lost from here to here will be equal to the, meaning that the difference in potential energy between these equal to total work done. So difference in the potential energy between points A and B equal to work done. Work done between A and B. So what is the meaning of that is half K and then x1 square, which is the potential energy, restant energy here, and here it will be x minus 1 subscript minus 1. This should be equal to Fd times x1 plus x minus 1. Okay, and what do we get? From here we get half K. Now this and this, so we get x1 minus x minus 1. Okay, will be equal to Fd, and what we get, x1 minus x minus 1 equal to 2 Fd over K. What it tells you here, ratio of the difference between this and this is 2 Fd over K. Similarly, if you go from here to here, again the difference between, from this logic, you will also find that x minus 1 minus x2 will also be 2 Fd over K. Same energy principle if you apply. What is the difference is? What is the difference is x minus 1 for the half time period. You have 2 Fd divided by K. For the other half also, this minus this will also be the same, basically, right? Hence, what you get? If you add them together, you get x1 minus x2 equal to 4 Fd over K, right? So, meaning, what is the meaning? From x1 to x2, from here to here, the difference is constant. Okay, what it tells you, from here to here has the same difference as here to here. It is the same difference, right? So that means here to here is same as difference between here to here. So this value and this value is same. Then how will this look like? This will be nothing but linear. This tells you that the peaks will follow a line, actually, right? Because difference between this and this divided by distance from here to here. Since distance from this here to here and here to here will be the same. This is the same wave. This is the same wave, right? Here, the magnitude of that, the frequency will be the same as natural frequency. Actually, it is exactly the same one. The only thing here is there is an energy loss. So omega n will be maintained in this case. It will not, omega d comes from omega, comes from the zeta, right? So omega n times 2 root under 1 minus zeta square. But zeta square, again, this is for velocity dependent thing. But here, this is does not depend on velocity. It is a constant. Fd is constant actually. So here, as such, in this case, zeta is equal to actually 0, because this is not the viscous damping. This is a different damping. Only thing is there is energy loss. Hence, omega n remains the same, but here there will be a resisting force which is equal to Fd, and you know that here to here is equal to here because this is time period, and difference between this and this, x1 minus x2 is equal to x2 minus x3 here. Hence the difference divided by time period, is both will be the same, hence the slope is same. Hence this will follow the straight line. So this will be a straight line. Okay. So a straight line. That's what we found out, right? This and this will be a straight line. Okay. However, it will go stop somewhere, right? So it will a spring here, you give a stretch and leave it. It will go for some time, and then it will stop when the applied force, the force will be because of the spring. When the total force, okay, is not able to actually provide the minimum force required to move. Minimum force required is to move is mu times n. If the force, the force which is being applied is less than mu n, then it will stop right there. Yeah? So it will not run for a long time. Okay, so whenever the force, applied force which is moving it is less than mu times n, okay, so in that case it will stop right there. So this is what it is about Coulomb damping, the system with Coulomb damping.